Hi Margie, I've got a couple of examples to go through with you. I think we won't attack the harmonic series just yet. We can look at that maybe a little later in the week if it comes up, but it might just be too much. So first of all, let's start with a projection. And we were talking about an example sort of like this, right? And so these are two vectors. We'll call that one V and this one U. And a projection is really just the shadow, like if you took the sun or a light and you shone it right down on it, then it's the perpendicular shadow that you would create. And so it's going to be in the same direction as V, but it's going to be a different magnitude, a different length than vector V. So what we're going to end up with is a new vector with two coordinates. If we're doing it, let's say in R2, we would end up with a new two-dimensional vector that is the projection of U onto V, because U is being like the shadow is going on. It's going to appear on V, okay? And so all we have to do for this is work out a few little things. We've got a formula that you'll have to memorize. And so if you're doing U on V like we are, then we're going to have to take the dot product of our two vectors. We're going to divide that by the magnitude squared of vector V, and then we're going to multiply that by vector V. So basically all we're doing is taking a fraction of vector V, right? It's going to go in the same direction, it's just going to have a different length or magnitude. So even if you wanted to, before you go into the formula, if you want to do some of your calculations, you could. Like you could do your dot product. Let's make up vector U and vector V, 4 and 3, and vector V, let's do 2 and 8 in this one. So if we do our dot product, we're going to have 4 times 2 plus 3 times 8. And that's going to be 8 plus 24 is 32, okay? Then the other thing we need is the magnitude of vector V, and then we're going to square it. So the magnitude is just squaring the length of our vectors. So we're going to square the x-coordinate, square the y-coordinate, and then we're going to square this as part of the formula. So we end up with the square root of 4 plus 64. And that's the square root of 68, root 68 squared. And of course, if you square a square root, you just get the number inside. So now we're ready to go into the projection calculation, and we've got all of our calculations done basically. On the top, remember we got 32 for the dot product. On the bottom we have 68, so that's our fraction, and then we're going to multiply it by vector V, which is 2, 8. And so we can reduce our fraction to lowest terms, 32 and 68, I think both divide by 4. Yeah, I think so. 8 times 4, 17 times 4. And we're going to just multiply that into vector V. And what we'll end up with is 16 over 17 and 64 over 17 as the coordinates of that projection. So we're not going to go all the way out to 4 or to 8. We're gonna have 16 over 17 and 64 over 17 for our new coordinates. Okay. So that's all there is to doing a projection. Projections are in 2 dimensions only, and so that's the only thing that you need to worry about. I'm just going to flip over to the next page and show you an example of where you would get a cusp and how that works a little differently. Sorry, I went through a whole long explanation and realized I wasn't on record, so we'll start again. All right, this is the cusp idea. I just wanted to give you a little example of this. Okay, so a cusp is a really weird one that doesn't happen very often, and it looks like the bird like that a lot of times. And so you're coming down to a very specific point here, and your slope, here our slope is negative, here our slope is positive for the two parts, but here what's happening is we have an infinite slope. Our slope is vertical right at this point. And so how we know that this is going to happen, and it doesn't happen very often, is if we set our first derivative equal to 0. So I've got my first derivative over here, and I'm going to write it with the x to the 2/3 in the denominator. So if I try to solve this for equal 0, there's no solution because it all goes out to 0. So that means that we don't have any critical points. Okay, so we don't have any max or mins in this graph. You can tell I'm getting tired, I can't spell anymore. So let's figure out what's going on here. When we look closer at this first derivative, one of the things that we notice is that before we get to 0, the slope is negative. After we pass through 0, the slope is positive, and we said that already by looking at the graph. But at exactly 0, the slope is undefined, right? Because if you put a 0 into the denominator here, it's going to make 1 over 0. So it doesn't go from a negative to a 0 to a positive, like a turning point does. It goes from negative slope to infinite slope to positive slope. And that only happens when you get a cusp. And that's something that takes a lot of experience to just remind yourself to look for when you've got a strange function like this that you're working with, okay? The other thing that you could do to get more information about this graph is to try to take the second derivative. And so if we take the second derivative of this, I would write it as y equals 1 over 3 x to the negative 2/3. That's my first derivative, and my second derivative then would be negative 2 over 9 x to the negative 5/3. And so when we have a look at that one, the same thing's going to happen, right? We're going to have minus 2 over 9x to the 5/3. And we can't set that equal to 0. And so there's no POI. It's not changing from concave up to concave down, which is important here. If we test some test points in this graph, when x is less than 0, this is going to come out negative, right? Yeah, y double prime is negative. And so therefore it's concave down. But when x is greater than 0, it's also going to come out negative. And so therefore concave down. And so if we got concave down both times, then that helps us with our graph, because if we know that it's got to be concave down till it gets to that point, and we know that after that point it's also concave down, then we know that it can't be doing this and then turning around and going back up like that. And so that's another indicator that we have something like a cusp occurring. So I'm not sure how much he's going to get into that with you guys. That's just sort of one example of what you would do if you came across it. But most people would not think to look at the denominator of the first derivative and realize that it could equal 0 and that we could end up with an indeterminate value there. So that makes that a really tricky example for curve sketching. I'd be really surprised to see that on like a midterm or a test.